All right, so today we'll look at definition of monads. We'll start with a review. We'll look at like the algebraic definition or the axiomatic definition of monads, and we'll do a bunch of examples. So I think I said this at the start of the first talk. I'm not going to use like analogies. We're not going to talk about how like a monad's like a burrito. We're not going to talk about like jQuery being a monad. There's tons of articles out there if you want to read analogies for what monads are like. I think, rather than getting kind of stuck in the confines of one of those analogies, I think it's better to look at just the pure axioms and then the theorems that get built up from the axioms. So anyway, let's start with our review. I will post a Git repository with the code that we're developing week to week after today. All right, so 2 sessions ago we saw functors. We saw how to summon functors via this syntax, and we saw like composing functors to get these composite structures, doing things like mapping over a list of options. Here, of course, we have a function that operates just on pure values, just on integers, and we were able to map that function over this nested list of option structure. Then last week we saw something similar with applicatives. We also wrote an applicative for both list and option. We were able to compose applicatives together. We were able to do things like call map2, for instance, where we had, in this case, we would have 2 lists of options. Let's just use the exact same list, for example. And we'll just sum each cell. Looks like I'm off with my parentheses. And here we saw, for example, our list applicative last week using this map2 syntax. We saw acted as like a cross product of the 2 lists. So we had like option 1 plus option 1, option 1 plus none, right? Option 1 plus 2, and so on. So I actually want to start with one of the things we did last week, and look at like the definition of applicative for list, and look at the bad definition that we started with, and try to see if we can make that lawful. Before we do that, though, I did want to point out that like map2, map3, map4, these were some of the first examples of like these free theorems or these derived functions that, as long as your applicative instance met the laws that we laid out, then you got these super really useful functions as a result, just by implementing the pure method and the apply method. We saw derived functions with functor, but they were all kind of silly, right? Like someone had asked when we talked about it, is that void method ever really useful? And even if it's useful, it certainly wasn't, surprising. You always, given a basic map definition, you could always have derived void anytime you needed it. Whereas things like map2, map3, map4, if you remember from last week, their derivation gets a little crazy, and yet they're like super useful. They show up all the time when just using regular data structures. And we'll see lots more examples as we go on as to how this stuff is useful. And I'm going to, maybe at the end of this today or the start of the next session, talk more about like literal applications of this stuff. So if you're not quite sure why we're doing all this yet, just hold on. We will definitely talk about that. But okay, let's look at our definition of the list applicative. And remember, here was our cross product based definition. And this is what we got to pass the laws. But we started with this other commented out definition. And the commented out definition, rather than doing a cross product, actually tried to line up the input list of A values with the list of functions and just apply them piecemeal, or index by index. So the first function was applied with the first A value, the second function was applied with the second A value, and so on. And as we saw last week, if we tried to implement this in that way, we got an error. Right? And it turns out it was the very first law, the applicative identity law, that failed. And let's take a moment to look at why that law failed. So the identity law says that for some f of a, so in our case, for some list of values, if we take the identity function and lift it into a list, so now we have a list of one element that is the identity function, and apply that list to our f of a's, then we have to get back what we started with. And so the first value that fails our test here, you can see, is a list of 3 elements. And so this makes sense, right? We start with a list of 3 elements, and then we zip it with a list of 1 element, just a single identity function. And hence, what we get back is a list of 1 element. It's just the first value. It's the singleton list that contains the first value. And that's why that particular entry failed to pass the test. So while we can't implement it this way in Scala, I want to show you how we can implement an applicative using this algorithm in a slightly different way. So let's just save off this algorithm for a minute. And the idea here is that at least to pass this applicative identity law, what we need to make sure happens is that if we come in with this list of 3 elements, we apply, we lift our identity function into f, into our list, we get back the starting value, fa. And so the real problem in our definition was pairing this algorithm with our definition of pure that lifts a value into a singleton list. Instead, what if we built an applicative for streams? So streams, for anyone that's not familiar, are similar to lists, except they can be infinitely sized, right? And so let's try to implement pure and apply for the Scala stream data type. Now, of course, we could do this and just create a stream of 1 element. And we could implement apply in a similar way. Let's just make sure we've got everything compiling. So everything compiles. And now let's try to test our stream applicative and see if it has the same problem. Now, of course, it should have the same problem, right? Because the difference between stream and lists here is just that lists are finitely sized. Streams can be infinitely sized. But there's really no difference in this particular example. So we should see a test failure when we run our applicative test for streams. So we're going to copy one of these tests here. We'll change this to be a stream applicative test. We have to implement an equality instance for streams. Basically, we have to teach our test framework how to compare as to whether 2 strings are equal. So I'll just do this real quick. And we're just, for now, going to just lift the definition we have for list, even if that isn't perhaps the best definition for streams. And you can see, of course, now our stream applicative fails our identity test, and it's basically the same problem. In this case, the first time it failed was a case where it had an input list or an input stream of 2 elements. But really, the very first test that has more than 1 element is going to fail. OK, so it seems like we just duplicated the same problem. But I said that the real issue with our implementation here was pairing this particular apply algorithm with this particular pure algorithm. And we already showed that those 2 algorithms were incompatible with lists. But it turns out that there is an implementation of pure that makes this lawful. And it's the implementation where lifting a pure value A into a stream, rather than creating a singleton stream, creates an infinite stream. Oops. So we would just write stream.continually here. So this will be a stream that has an infinite number of elements, and every time you ask for the next element, you get this input value A. Because of that, when we lift the identity function into stream, we get an infinite list of identity functions, and each one of those are applied piecewise to this input stream here. So let's see how we're doing. So what's happening in this case, you can see here the Java process. We're at about 600% CPU. And it's doing lots of equality tests on very, very, very large streams right now. If this ever finishes, it will have passed the applicative laws. So I'm actually going to remove our test for this case because I don't want to wait for this to run every time we go through the monad examples. But nonetheless, the point is that
Can you limit the size of the stream?
You could, yeah, you could do it in Scala check, sure. And in fact, I don't know if in Scala check, I don't know exactly where we're hung here. Is it the input stream size, or is it like my silly equality comparison is actually running for all and calling through an infinite stream or something? But you can see it's really really busy. So yeah, it's zipping an infinite stream right now. So anyway, I'll actually kill this and turn that off. But that is a lawful definition, and it's worth pointing out that a lot of these ideas, a lot of these structures that we're looking at do originate, at least in the programming world, in Haskell. And in Haskell, the applicative instance for list is defined as the cross product, but they have an alternate applicative definition for lists that's defined this way. And Haskell can do that for list because its lists can be infinite due to lazy evaluation that's built into the language. Okay. And we'll see other examples as we go on. Maybe not today, but in a few, I think the next lecture, we'll see examples of other data structures that have multiple applicative definitions. And depending on the use case, you might want to use one or the other. Okay. So let's now look at monads. We'll start with a new file. And the encoding of monads that we'll look at today, we're going to do with two operations. We're going to use pure, just like we did in applicative. In fact, I'll just lift the pure method directly from applicative. So this is the exact same idea of pure. We're just lifting a value a into our context f. And then we're going to define flat map, which says given an f of a and given a function from a to f of b, we get back an f of b. So these will be our two abstract methods that we'll define on a monad. So we saw when we wrote applicatives that we were able to show that an applicative is a more specialized form of a functor, right? It was it had the general rules of a functor, but it also had this more strict definition where the map operation had to behave a certain way as it relates to pure imply. And so we can do the same thing with monads. The way we'll encode that today is we'll make monad extend applicative. Now, so pure will pick up from applicative. That's fine. We're going to leave that abstract. And we're, flat map, we certainly going to have it abstract. But we're going to have to implement apply to show this relationship. We're also going to need some laws, which we'll show as well. But let's implement apply from applicative in terms of flat map. So here is our apply signature. We said that we had some f of a, and we had a f of a to b. We had to return an f of b. So this looks similar, but not quite the same. So the question is, how can we use flat map here to implement this particular signature? The way we're going to do it is we'll call flat map, but for the first parameter, rather than passing f of a, we'll just pass f of f. So what that means is now we need to pass a function, and our input to our function is going to be another function. So here, our closure here, we're going to get a function.
F of f, sorry.
Yeah.
F of f is, how does that work? So, wait a minute. Yeah, how does that work? Don't you need to pass f of a to flat map?
Well, so flat map is defined for any, right? This a is defined for any f of a. It's not this a, right? These are unrelated a's. Yeah. So basically what we're going to do here is say, take this a of b and substitute it into this a. Again, like think of a different namespace here. But so if you will, replace every a with this other a prime to b prime. And what we end up with here ends up being a function from a to b as input, and we have to return an f of b. Well, so, and actually, you know what? Let's change our names just to make this a little easier to follow. In apply, we'll just change these names to x and y. All right. So now what we have here is a function from x to y. Okay. So inside of this function, where these question marks are, we have a function from x to y, and we haven't used fx yet, which is an f of x. And we need to turn this into an f of y because we want an f of y on our output here. We know whatever we're passing here overall as a function needs to return an f of something because we're calling flat map, and flat map requires that our function returns an f of something. So we can set b equal to y, per se, like just algebraically. And hence this inside, if we simplify all this inside expression has to return an f of b or an f of y, right? Because we set b and y equal to the same type. So again, we have an f of x, and we have a function from x to y. How can we convert an f of x and a function from x to y into an f of y? And we saw that the first week. We have map. So we can map over fx, the function f, and we end up with our implementation of apply. So if we save that and look at SBT, you'll see that that does in fact compile. If I had implemented it correctly. And normally this would be fine to do, renaming these types here. The reason that didn't compile is because of simulacrum. Some of the annotation stuff it's doing in generating all of the helpers ended up being broken there. Oh, sorry. We saw this last week as well, right? When we implemented map in terms of apply and pure, we needed the override keyword. When we implement apply in terms of flat map and map, we also need the override keyword. All right, so now it did in fact compile. Let's write another derived method. So we just showed that at least type signature-wise that we can define a monad as a more restricted form of an applicative, right? Something that's an applicative but that has this additional flat map operation. And now we can show some derived methods that are specific to monads. So one of the most common derived methods would be flatten. So flatten would take like an FFA, oops, would take an FFA and just return you an F of A. So this is like you got a list of lists. You want to flatten all of those inner lists into one big list, right? We can implement this in terms of flat map. So we'll start by calling flat map passing FFA. So now in here, what we get as an argument is an FA. And if we just return FA, we get this as the output, right? Like here's in flat map, if we have an FB as our output of our function, we overall get an FB as an output. So flattening is really just flat mapping with the identity function, and we can even write it that way. We can also provide a specialized form of our map function. We don't have to, like we used map already, we're using it here. Because map's implemented in terms of pure and apply, and we're extending from applicative, we get a map function for free. But often, you'll get a little bit of a performance bump if you implement map in terms of pure and flat map instead. So let's write out what our map looks like. We have a function that takes an f of a and takes, it takes an f of a and takes a function from a to b and returns an f of b. We'll flat map on fa. And now what we get here is an a passed to us. The function is an a. We have to return an f of something. But if we just call f of a, all we get is a b. And a b is not an f of b. And so we seem to have a bit of a problem, but of course we can wrap that b via pure into our type constructor f. So it's just a slightly different way to implement our map function than what we saw in the apply case. If you recall from last week, we implemented that as applying our pure function. And this way we'll implement it with flat mapping. So let's take a look at the monad laws, because we need some laws that guide what legal implementations we have here of pure and flat map together. We'll just actually, I want to take all of this as a starting point. So I just copy and pasted our structure, and I'm replacing the term applicative with monad everywhere it shows up. All right. There are three laws we care about with monads. The first law we'll look at is associativity of the flat map operation. So we're going to take three types, A, B, and C. We're going to take an f of A to start with, a starting value. And then we're going to do two flat maps. So we're going to take a function f that goes from A to f of B. We're going to take a function g that goes from B to f of C. And basically what we're going to do is apply, just like we did with map associativity, we're going to apply f to f of A via flat map, and then we're going to flat map g. So let's do that first. And we're going to require that that equals the result of flat mapping them, or distributing the flat map, the second flat map inside the first function. So what I mean by that is we're going to do fa.flatmap, and we're going to use f inside of here. But there's one problem. Oh, there we go. So we're going to use both f and g inside of here. So if we have an a value here and we have f that takes an a to f of b, we can call f passing a to it. And of course, we get back an f of b. That's just normal function application. Then we'll flat map on the result of that. And now in here, we'll get a b, and we can just call g of b. So you can see in the first case, the flat maps were sequential. And in the second case, the second flat map was inside the first flat map. So this will be our first law. We have two more laws, and they're basically two different types of identity laws. So the first we'll do is left identity. To write the left identity law, we're going to require a value a. We're going to require a function from a to f of b. And basically what we're going to do is lift our a value into our type constructor via pure. And then we're going to flat map f. So we're going from an a to an f of a, then we're flat mapping this a to f of b, so the resulting expression here is an f of b. And we're going to require that that has to be equal to the result of just applying a directly to f, right? Because we have an a and we have an a to fb. We have one final law that we're going to require monads to implement. Here we only need one parameter. It'll just be f of a. And we're going to flat map pure effectively. So, of course, flat map, we have this pure a value. We're going to lift that into our type constructor via our pure method. And we're going to require that the result of doing such a thing gives us back our original input. So these will be our three monad laws. And really, this is all that a monad is pure and flat map, these two functions with these exact type signatures, such that the implementations adhere to these three laws. So again, if you want to know how a monad is like a burrito, please check various articles on the internet. But really, it's nothing more than two abstract methods that adhere to these three laws. So let's try to write some monad instances and make sure they are lawful. To do that, we're going to start with, we'll just copy and paste our applicative test. This time I will actually use find and replace. We'll have to implement our three properties the way this code structure. We have to re-implement them here. So we'll real quickly do flat map associativity. Flat map associativity took 3 arguments, if you recall. So we're just going to say, give us some arbitrary f of a, give us arbitrary functions a to f of b and b to f of c, and we're just going to call our flat map associativity function and then ask if the results are equal. Let's add our next 2 laws very quickly. We'll do monad left identity. And finally, we'll do monad right identity. Okay. Let's make sure we transcribe that correctly. We should have a couple errors. The first is just an import issue. And it's actually an import issue in our file over here. It's complaining because we don't have pure in scope. We're using like pure right there. We're using pure right here. We can get pure off of our f instance here. So we're going to actually change this to be a val. That way we can do import f.pure. Let's see what it's complaining about now. Line 39. Let's make it a val down here as well. Okay, so now we get some compile errors in our tests, and that's because we've changed what arbitrary instances we need. So let's go back and make all of those work. Let's see here. We want to replace, let's say, all A's with integers. This test was implemented where like A, B, and C were predefined up here. So we'll make all of our A's be integers. We'll make our b's be strings. And finally, we will make our c be a long, let's say. That should get us most of the errors. We're down to 2 errors now. Here it's having trouble finding an arbitrary instance for the tuple int comma f of string. Really what we need to fix this is, let's see, we're going to need an f of long. So basically what we're doing here is saying that in order to generate an arbitrary function from int to f of string, Scala check is going to require an arbitrary int as well as an arbitrary f of string. So we're going to ask for an arbitrary f of string. We're going to ask for an arbitrary f of long. And down here, we're already asking for an arbitrary f of int. So we just need to ask for those 3 arbitraries here. All right, let's see how close we are. All right, so we're down to 1 error, and this time it's saying it doesn't know how to compare f of longs for equality. And you can see here we asked for equality instances for f of ints and f of strings, but we need one for f of longs. All right, so finally I think we'll have our tests compile. All right, so everything's compiling, but we need to define some instances to check to see whether those instances are lawful. So we're going to write instances for both list and option again. And we'll put them in the monad companion object, since that's what we were doing earlier. All right, so our first function for list will be pure, and we're going to use the exact same definition we used for the lawful applicative instance for list. That is, we'll return a singleton list. For our flat map definition, we have it nice and easy. Because the list data type defines flat map directly. So we can just do like fa.flatmap of f. It's worth pointing out that like the flat map method on Scala's list does not have this exact signature. Let's take a look at what the actual flat map method signature looks like on list. So this is a lie, but that at least it looks similar. You can see it's a lie because it has this use case thing here, right? Which is basically, Scala parlance for the fact that this is a simplified signature to what it really is. But you can see like even this signature is not the same as our flat map signature for monad. Our flat map signature for monad required that the function return a list. And here you can see that all you need to return when using the collection library's flat map is a gen traversable once. Now, of course, list is a subtype of gen traversable once. But with our flat map definition, you can't return, let's say, a set or some other collection type, whereas in the standard library you can. Again, this is a lie, so let's look what the real flat map definition looks like. Here's what the collection library actually looks like. You can see it's quite a bit more complicated. The function is still A to gen traversable once B, but we've got this weird can build from here. And then our return type is even stranger. Rather than getting like a list of B's back, we're getting a that, where you can see that shows up in the can build from, right? This is how you can go like from a list to a set, for example, via flat mapping, or like a list to an iterable via flat mapping. But again, we're not allowing any of that. Our definition of monad is much stricter than any of that stuff. Okay, so there's our list monad. We're going to copy and paste this for our option monad. And we could implement it the same way, where we just lift the value directly into an option, and we'll use options flat map function. So with that definition, you can see here our list monad passed the 3 monad laws, and our option monad passed the 3 monad laws. Let's try to use this at the REPL. So if we have the monad for list, we can, let's say, flat map. We'll have we'll flat map on the list 1, 2, 3, and given one of the values x from that list, like the number 1, let's just return a list of that many number of elements. Right? So like if we get 1 here, we're going to return a list of 1 element using the value 1, if that makes sense. We get a 2 here, we're going to return a list of 2 elements where both of those 2 elements is the number 2. And you can see this behaves just like flat map in the standard collection, of course. You get 1, 1, 2 2s, and 3 3s. They're all concatenated together. All right, so let's do the same thing with the monad for option. Maybe this time we'll say, like if x is greater than 0, then return some x, otherwise return none. You can see, of course, flat mapping 1, we get some 1, and flat mapping, let's say, none, we get none. So, so far, this definition isn't maybe particularly exciting. What have we accomplished by extracting out this definition? Well, we have the minimal definition of a monad in Scala, and now we can abstract over type constructors. So we can work, we can write functions that take any arbitrary type constructor f, as long as they are legal monads, and do things like flat map them. So we're going to see this extensively as we move forward in subsequent weeks, where we can write algorithms that work for any old monad type, not just like any old collection type like the Scala standard library, but can work arbitrarily on any collection type. On any monad type. One thing we did, though, with both functors and applicatives, is we defined the composites, where we were able to like create a functor, or take 2 functors and compose them together to create like a functor from f of g. We did the same thing with applicatives. So let's try to do that with monads as well. So we're just going to take this boilerplate. And we're going to put it here, and then we'll just change applicative to monad everywhere. So if we have a monad f, we're going to compose it with another monad g. And what we want back is a monad for f of g of x. All right, so let's think here. what our flat map signature needs to look like. So our input should be an f of a. Well, our f down here in compose is really f of g. So our input's going to be an fg of a. So that part's OK. Then our function type needs to be an a to f of b. Well, so our function type down here will be a as input. And now it needs to be an f of b, but again, our f is really an fg. So this should be an f of g of b. And we should return an f of g of b as a result. So let's make sure we got that syntax all right. So far, so good. Everything's compiling. So the question is, how can we implement this flat map method? Like pure, we've already implemented, right? Since I stole pure from Applicative, since we took pure from Applicative, we had an implementation here that makes sense. So all we need to do is write flat map, and we've got this composite monad. Well, let's look at what we did with Applicative. We started by saying, like we mapped FF, we mapped over FF using some function, and then we flipped our Applicative, right? This was pretty complicated, but we came up with this last week. Let's look at what we did with functors. Functors were pretty easy to work with. We just did nested mapping. We mapped on the outside f of g of a, and then mapped on the inside. So how can we do this one? And we have the full bevy of methods here to use, right? We can use like f dot flat map, of course. We can use f dot apply, or map2, or map3. Or just map, of course. Everything we've built up so far, we have access to here. So maybe like one idea is like, well, we have this pure function f. We have to, we have to somehow get an a. So we have an a way down deep in here. We could start by saying, like, what if we took fg of a, mapped over that? That would give us a g of a. We could take g of a and map over that. That would give us an a. All right, so now we can apply a to f, and then we have from that an f of g of b. But think what we have overall. Like we're returning an f of g of b from this map called a g of a. So now this overall map expression is going to have type g of f of g of b. And we're returning that g of f of g of b from this overall map expression, which is on an f. So what we end up with here is an f of g of b. And if I did all that right, we should compile. Let's see here. We haven't imported our syntax, so we'll have to say import monad.ops. I'm not seeing what I'm missing here. Type class monad. Well, anyway, I'll just do it this other way. We'll say f.map. And here we'll do g.map. We won't use the OO syntax. Oh, and of course, this should be self. And I think it'll compile now. OK. So the point is we succeeded in using our function, but we have this weird type f of g of b. This is sort of like something we could use with flatten, kind of. Right, our flatten method takes nested f's and converts it to a one-level f. And remember, our f is fg down here in the composite one. So it seems like maybe we should just be able to flatten this. That compiles. So let's see what happens if we try to use it. So let's go over here. So we're gonna write a test for list option. And we're gonna need those type lambdas in order to write this out. So we're gonna say lambda x is going to be a list of option of x. I'm missing some brackets. This will be a little painful. Basically, it's saying it can't find a monad instance for list of option. That's because we don't have it available implicitly, so we're going to have to pass it explicitly to our constructor here. So we're going to do that by saying monad of list compose with the monad of option. Now, unfortunately, we also have these other 6 implicit arguments, and I don't want to look any of these up. So we're just going to write implicitly, and hope the compiler accepts this. 4, 5, 6. Okay, so it compiled. But look what happens when we try to run it. First, we have an associativity problem. You can see here it found, well, actually it was an exception that was raised. It called it with 3 arguments and some exception was thrown, and it was a Stack Overflow. Oops, where did it go? We had this Stack Overflow error here. And the next one, left identity, also had a Stack Overflow. Right identity had a Stack Overflow. If we look at what the Stack Overflow is, it's not going to give it to me, is it? Well, it's not going to give me the Stack Overflow. Let's try it at the REPL then. So we'll start with a list of options, just like we started the day with. We'll just do 2 right now. And then we have a number, x, and we need to return a list of options. So we'll just do something really simple, like return list of sum x. And you can see what's happening is that by using flatten, we were just flat mapping. So basically, we defined 2 methods in terms of each other. Right? We defined flat map in terms of flatten, and we defined flatten in terms of flat map, and so we just overflow the stack. We had 2 mutually recursive functions that never actually make any progress. So we tricked ourselves in this monad definition by using flatten here. And overall, no matter what execution path we take here to this definition of flat map, we're not going to be able to find a definition that satisfies the laws. So unlike functors and applicatives, monads cannot be composed together into a larger monad. Certain monads can. So, for instance, we could, if we know something specifically about the list monad, like we know we're working with the list monad, there is a way to write a composite monad that says, take the effect of non-determinism from the list monad and combine it with some arbitrary other monad, any other monad in the world, as long as it adheres to the monad laws. And yield as a result a new structure that has the effects of both non-determinism from list, as well as the effects of this other arbitrary monad. And the result will be something that passes the monad laws. Right? So the list monad is an example of a structure that lets us compose with some arbitrary other monad. The option monad also has that property. So you can write code that takes advantage of the option monad and composes it with any other arbitrary monad to yield a new monad that does both the optionality effect, the idea that like you're working with functions that can fail at any point with a none, with some other arbitrary effect. But you can't do that with two arbitrary monads, right? You have to know something more about the first one in order to generate a composite. It's also worth pointing out the things that you can't do, or other things you can't do just with monads themselves, ignoring composition. For example, like if you know Scala 4 comprehensions, we have map, we have flat map. We've now implemented both of those. The other big feature in 4 comprehensions is filtering. But monads do not support a notion of filtering. We can't define, or to crystallize that, we can't define a function filter AB A to Boolean. You might be tempted to try to define this function. It is impossible to define this on monad. So if you want to try, please do, because I think it's a good exercise to try to go through and make this compile. But basically, you just don't have enough information about either the type constructor f or these values a in order to implement this signature. Right? The only thing we know about f is that we've got pure flat map, map apply, all the derived functions. And we know nothing at all about A. I should point out that to actually implement these in a legal way, you can't even use things that the JVM exposes to you, like toString or equals or hash code. You just kind of ignore that they're there. So we know absolutely nothing about A. It's completely opaque to us. And as a result, there's just no way to do this, right? You might think well, what if we took f of a and mapped over it, something like map fa. Now, of course, if we did this, what we end up with is an f of Boolean, not an f of a. So that's not quite going to work. Well, maybe the idea is then to flat map. So if the function passes, then we can return pure of a. So that looks good so far. Flat mapping and returning a pure is just like the way we define map up here. So that part's good, but if you try to define the failure case, you're kind of in trouble. We don't really have a way to say, get rid of this entry. Yet notice that implementing filter here for a list is really simple, right? If we were implementing filter directly for a list, we would just say else nil. And if we were implementing it for an option, we would just say else none. And so there's further extensions we can put on top of monads, add even more abstract methods with more laws as with how those abstract methods interact with the other methods that come from monad. To build up things like filtering, and eventually to build up things like, being able to do concatenations of values and all sorts of fancy things. But those will be future talks. One final thing to say today, and then just any questions I'll take, is that this is one way to define the monad structure. There are other ways to define it. So basically, another way to define it is that you keep you keep pure and flatten as your abstract operations, and you can derive flat map as a result. In Scala, we typically do it this way, where we keep flat map as the abstract operation and then derive flatten. It's mostly stylistic, although I think the reason in Scala we do it this way most frequently is that when we implement all of the collection types, it's convenient to be able to delegate directly to their flat map operations. And most of the collection types, if you implement or if you use their flat map operation, they have a corresponding pure implementation that is legal. Although not all collection types are like that. So famously, the try type from the Scala util package is not does not pass the monad laws. Sets don't even pass the functor laws, as we've talked about. Yet sets have a flat map method. And clearly, if I should point this out, if you don't pass the functor laws, you clearly are not a monad, right? Because every monad is a functor. And hence, if you fail the functor laws, you can't be a monad either. Okay, so I'll open up for questions now. I will say next time we'll probably look at some of the examples of composing monads together, where we take advantage of knowing something about the starting monad. Like, so how do you take a list monad and compose it with some arbitrary monad to create something fancy? But anyway, are there any questions? Yeah, so one question came in is that if the monad was also a monoid, couldn't you implement filter? And the idea there is that we need this empty value, right? Something to say return empty. So let's just type that in. Let's just put the word empty there. If we could define this empty thing in terms of a monoid, then yes. We have a bit of a problem, though, in that we've got a kind issue. Right? Remember when we talked about kinds in the first week, we said that we had proper types, things like int and string and list of int. Those were all proper types. We could actually take an expression and say this expression has the type list of int. And we said those were kind 0. Then we said we had like type constructors of one argument, like list and option, which had kind 1. Monoids are in Scala, we define a monoid as a type class that abstracts over proper types, right? So we'll say something like a monoid on type A, right? No fancy type constructor there. That's kind 0. Is going to define something like a combine method that takes two A's and returns an A, and defines some identity method that returns an A, such that like X or combining X with identity gives you X, and combining identity with Y gives you Y. We're also going to require that combine is associative, right? So combining X and Y and then combining Z is the same as combining X with the result of combining Y and Z, right? So that's our typical monoid definition. And now notice that we've got this kind issue, that monads are defined over kind 1, monoids are defined over kind 0, and we have a bit of a problem as a result. So it's like, in order to define this filter, we need an empty f of a. So like maybe you'd be tempted to say, we'll just ask for like, add an implicit, say, give me a monoid for f of a. And then we could say like mfa.empty, or sorry, .id. And you can implement filter in this way. This is one possible way to implement filter. It turns out that there is a much more general structure, which we'll look at in a subsequent week, where we can talk about like a monad that is that also has this property of the type constructor generating arbitrary monoids for any type A we stick into it. Right? Like a list can always give you a monoid. Right? A list can give you a monoid for any type A. A list int, the monoid is just list appending, and the identity 0 is just, I'm sorry, the combine is just list append, and the identity is the empty list. Same thing with options, right? You can define like a free monoid on options that combine is just taking the first element, and the identity function is just, or taking the first defined element, so basically x or else y, and the identity function is just returning none. So anyway, there's a set of structures that are both monads and higher kinded monoids, and we'll look at those in a few weeks.